Welcome to the pointer analysis part of the second lecture in the third module on general data flow frameworks. In this part of the lecture, we are just going to introduce pointer analysis by looking at the broader perspective. So here is an outline of what we are going to do in the entire coverage of pointer analysis. But today we will focus primarily on the larger perspective and comparing points to and alias information. Later we will define points to analysis formally, then we'll look at flow insensitive points to analysis, we'll talk about flow sensitive points to analysis, and then we'll talk about liveness based points to analysis. Generalizations to heap, array, pointer arithmetic and union are left out of this particular offering of the course. So here is an interesting question. The question what we're trying to do here is ask why pointer analysis is important. And so the question that we want to ask here is, the interesting question that we want to ask here is P arrow data live at the exit of line 5? The program has initial assignment Q is equal to P. There is something in P, and then there is a while loop that traverses the pointer Q. So which means that presumably we have a linked list rooted at P, and we said Q is equal to P. So we get a current pointer to P, and then we keep going traversing the next pointer. And at the end of this traversal, now we say P arrow data is equal to R1. So we are writing into P arrow data, but we're reading from Q arrow data. So P is the head and Q is the current pointer, which is moving in this particular loop. So we are writing in P and reading from Q, and we are once again writing in P. So we are writing P arrow data equal to R2. The question is this live at the so at the exit of line 5, do we have P arrow data live here? We are writing into it. But is this live? If it is not live here, then the assignment on line 5 is dead. So basically we are asking a question: is there a use of the value being written by assignment 5? The answer is not so easy, but if you understand the program very well, you will find that indeed this is live. We cannot guarantee that P and Q are distinct. In order to make this distinction, we change the program a little. Now we change the loop to a do while loop. So we say do move the pointer while certain condition is met. In the earlier example, we have this while loop. So the question boils down to asking what is the essential difference between a while loop and a do while loop. And if you are a good programmer, you would know the main difference, which is the while loop may not execute even once, whereas a do while loop is guaranteed to execute at least once. What that means is, when we have a do while loop, this Q is guaranteed to have moved to Q arrow next, and therefore P and Q would not be aliased. We know for sure that P and Q are not aliased. Whereas when we have just a while loop, we cannot say statically how many times this while loop would exist. And so there is a possibility that at the end of this loop, Q might point to this node, or it might point to this node, or it might point to this node, which means that Q and P may well hold the same address, and so Q and P may be aliased. Whereas when we have a do while loop, we can guarantee that Q and P will never hold the same address in this program, and they cannot be aliased. However, there is still a small catch when we make this statement. And what is the catch? We cannot delete line 5 if P and Q can be possibly aliased, and P and Q can be possibly aliased if we have a while loop, or even when we have a do while loop, P and Q may be aliased. If we have a circular list, if we keep going next and some next points to this, then P and Q may be aliased. So which means that answering questions in presence of pointers is non-trivial. We can delete line 5 as a dead code if P and Q are definitely not aliased, which is possible when we have a do while loop and the list is not a circular list. This brings out the importance of figuring out information about pointers. Here is another example of code optimization in presence of pointers. We are writing a value 5 in A and we are storing the address of A in X, and then we are making this assignment B is equal to star of X. This is the original program. If we did constant propagation that we have seen in the previous in the beginning of this module in the previous lecture, then we will say that look, we don't know what this X points to, and we will not be able to say for sure that B is equal to 5. So constant propagation will not optimize this program. However, if we had the information that X holds the address of A and therefore star X actually reads the value in A, we will be able to do this optimization B is equal to 5. So the point that I'm trying to make is pointer analysis provides useful information which makes other analyses and other optimizations more precise, more accurate, more effective. Pointer analysis on its own is not an optimization. It's not an analysis that gives you some information that can directly be used for an optimization. There has to be some optimization that we are doing, and that optimization is prohibited because we have indirect references. Pointer analysis can provide information about the indirect references, thereby resolving the indirect references, making it possible for other analyses and other optimizations to derive useful information, more useful information out of programs. Here is another interesting example of the kind of optimizations that we can do, and this brings out a range of things that we have to keep in mind when we do points to analysis, or a range of things that points to analysis can enable. So here we have the main program which calls procedure F. Procedure F does an assignment P is equal to G. Note that P is a pointer to a procedure, so a call is being made using P, and we could have P pointing to either G or P pointing to H. So we have P is equal to G, and so when we call F, we do P is equal to G, and then we are calling P, and the question is once again, is B can we do the optimization B is equal to X? We can do this optimization provided X is assigned the address of A. Here we are assuming that all the variables are global variables. If X is assigned the address of C, then we cannot do this optimization. So what we have to understand is the call to F does this assignment to G, which means that P is going to call procedure G and not procedure H, which means that this optimization can be done. So we have to do analysis of not just data pointers, but analysis of function pointers as well. And there are some differences between data pointers and function pointers. So what is pointer analysis? Pointer analysis answers the following questions for indirect accesses. Which data is read? For example, when we have x is equal to star y, what am I reading here? Which data is written? For example, we have star y, star x equal to y. Which location are we writing into? Which procedure is called? For example, we have a call to P or a method call on a receiver object X. So these are the questions that are answered by points to analysis, and by now you have written several programs and you know that your programs would typically have statements such as these, and therefore in order to make any program analysis effective, pointer analysis becomes very, very important. In particular, pointer analysis enables precise data flow analysis and precise interprocedural control flow analysis. So computationally intensive analyses are ineffective when supplied with imprecise points to information. For example, model checking, interprocedural analyses. So if you don't know which procedure is being called, you will have to assume that all possible procedures are being called. If you don't know which pointer is being written into, you will have to assume that all pointers are being written, or all data locations are being written into. If you don't know which pointer is read, which location is being read, we will have to assume that all possible locations are read. So this increases the size of the data space that any analysis has to consider. So either it becomes non-scalable or inefficient, or it becomes ineffective because it has to consider a gross over approximation of what actually is happening. In order for pointer analysis to be useful, it needs to scale to large programs. For small programs, there isn't much challenge. Pointer analysis can be done using what we are going to study here, but our interest is more in how can we scale it to large programs, and that has been an important goal of the research being done in my group at IIT Bombay. So the world of pointer analysis consists of these three kinds of things, and there are two different names for it. Somewhere it's called alias analysis, somewhere it's called pointer analysis. So when we talk about pointer analysis, we are talking about data pointers, alias analysis of data pointers, or points to analysis of data and function pointers. So what do we mean by points to analysis? By points to analysis, we say that this pointer points to this location, or this pointer holds the address of this location. By alias analysis, we say that these two pointers hold the same address, and we will compare the points to information and alias information more precisely as we go along in this particular lecture. On the other hand, we may have no pointers, but we may still do alias analysis of reference parameters that are passed through addresses. There is no explicit pointer, but languages like Fortran allow reference parameters. So we can pass parameters using references, or even in C++ we can pass parameters using references. So there could be aliasing between the formal parameters, because the same parameter is being passed as same actual parameter is being passed in two different formal parameters. There could be aliasing between fields of union. There could be aliasing between array indices. So we may not know when we use AI and AJ whether the ith index and the jth index mean the same index. So that leads to the possibility of aliasing between array indices. We are going to focus on points to analysis of data pointers. So pointer analysis collects information about indirect accesses in programs. It enables precise data analysis. It enables precise interprocedural control flow analysis, and it needs to scale to large programs. There have been several papers in past. People have often wondered about the pointer analysis. The generic papers, philosophical papers, which try to answer questions such as, which pointer analysis should I use? Which pointer analysis is good for me? This was a paper that was published 20 years ago. And then there's an interesting paper called Pointer Analysis. Haven't we solved this problem yet? This was the paper published in 2001. We are in 2020 and the answer is we still haven't solved this problem if we talk about scaling point analysis to large programs, and that has been the focus of my group here at IIT Bombay. So the mathematics of point analysis is very, very pessimistic. There are lots of results which say that in the general situation, alias analysis is undecidable. Flow insensitive alias analysis NP hard, points to analysis is undecidable. So what mathematics is telling us is that we should forget about getting a precise answer of points to analysis. We have to adjust our expectations suitably to avoid disappointments. And because mathematics is pessimistic, engineers have jumped in. So what should we expect in the engineering of point analysis? To quote Michael Hind, what he says in his 2001 paper is that although points to analysis is undecidable, fortunately many approximations exist. But he goes on to say that unfortunately too many approximations exist. In fact, as it stands now, there are as many versions of pointer analysis as there are pointer analysts, and each expert in pointer analysis has their own favorite method of performing pointer analysis. So what I'm trying to say is that engineering of pointer analysis is much more dominant than the science of pointer analysis. So what is the difference between engineering view and the science view? The engineering view is to build quick approximations, which is governed by the tyranny of exclusive OR. If you have friends and acquaintances in the corporate world, you would have heard this phrase, tyranny of OR, and we mean exclusive OR. We cannot get everything, so should we go for this or should we go for this? In case of points to analysis, the choice people believe is between precision or efficiency. Can I get a precise pointer analysis or can I get an efficient and scalable pointer analysis? Science view, on the other hand, builds a clean abstraction and it asks a question, can we harness the genius of AND? Can we get precision and efficiency? And as I've been saying, this has been the focus of the research in my group here. So most common trend as evidenced by publications is to build acceptable approximations guided by empirical observations. So most papers on points to analysis will come up with some idea and will say because of this I get 10% more improvement or 20% more improvement, etc. So what is acceptable is something that is often constrained by beliefs rather than the possibilities of what could be done. And therefore we need to make a clear distinction between approximations and abstractions.